Hello, I am Jung Ge. I will talk about the vulnerability in the desktop window manager. It's me, and now I am researching the vulnerability on Windows and macOS at Theori, Korea. This is the content of my presentation. The content is very simple. After introducing the structure of desktop window manager, I will explain a real vulnerability case, and then I will conclude my presentation. Desktop window manager is the system service for managing the all windows. It is added from Windows Vista, and it is used for applying several effects such as transparency. This component is highly related with direct composition, which is in the Win32k, the kernel. Because DWM is related with direct composition, it will simply cover about direct composition a little bit in this presentation. But because it is not the real target of this talk, if you want to know more information, you can refer below these links. DWM process is served as DWM user. DWM user is system integrity user and can access all other window handles. By using anti-user get Windows process handle, DWM process can get owner process handle from any window handle with desired access. From the process handle, we can get the code execution by using DLL injection or code injection. In addition, some system calls are only permitted to DWM process. Because these system calls are only permitted to the DWM process, the validation seems to be weak. For example, the anti-decomposition duplicate handle to process, this picture shows that, is only accessible by DWM process. That is checked by this user is current process DWM function. But before calling this OB duplicate object, there is no validation for the third argument. Yes, so we can write 0 or handle value to arbitrary address. The crash is like that. But the post-exploitation after getting DWM user privilege is not the topic of this presentation. So I will cover until getting DWM user privilege. This picture shows the overall structure of direct composition and DWM process. By using the several APIs and system calls, users can create several resources on the kernel, like the C-filter effect marshaller and so on. After creating several resources on kernel, these resources are serialized and sent to DWM process by LPC. Finally, DWM process merges the several effects and apply them to screen. The system calls related with direct composition can be easily distinguishable because the name of system call starts with anti-decomp. This picture shows the several system calls related with direct composition. Among several system calls, these three are important for this talk. The first is anti-decomposition create channel. It will create the channel to communicate with kernel. The second is anti-decomposition process channel batch buffer. It will send several commands for created resources. And third is anti-decomposition commit channel will serialize the resources and send them to DWM process through LPC. So that is, it will commit the data to screen. So you can use direct composition in this order: create channel, send message, and commit the message. And the message also has several kinds of commands. This below picture shows the list of the commands of direct composition message. Among them, create resource command is used for creating resource. It will allocate new object according to the resource ID, and the create object has own virtual function table. After creating resource, you can send several commands to the resource. Each command has corresponding function in the virtual function table as shown in this picture. Thus, if you send the command, it will trigger the corresponding function. For example, you can send the set resource float property. It will the set float property method of that resource. So let's dip into real code. This code shows the corresponding function for the set integer property command of HWND bitmap modular. When you update the data for a resource, it will do two things: set a flag for serializing and store the data. As shown in this picture, it sets the flag 0x20 at 0x10 offset and store the value at 0x38 offset. After calling proper function, such as set integer property, for the resource, if the data is successfully updated, the resource is added to the list of channel objects. This list contains the resources that will be serialized. That is, the only successful commands will be serialized. And then users call the anti-composition commit channel system call to send the data to DWM process. This system call serializes the several actions, such as creation, or deletion, or update data for resources. Serializing for updating data command is handled in emit update commands function, which is shaded as yellow, and it will call a emit update commands method of the virtual function table of the resource. The emit update command method first checks the flag value, which is updated before. If the flag is valid, it allocates the memory for storing the serialized data. The offset 0 of serialized data has the size, and the offset 4 has the command number. 0xbc is in this case, and this serialized data will be sent to DWM process through LPC. Now switch it to DWM process from kernel. DWM process retrieves the serialized data from kernel, and the data will be handled in this function process command batch. In this function, after validating the size, then call the process message function. Process message function has switch statement for handling each command. In this case, the command number is 0xbc, so this picture shows the handler of command 0xbc. It will retrieve the HWND bitmap object by using a resource ID and call the process update function. Finally, the serialized value is stored in the object and it will make the real effect. So again, check all steps to send the message to the DWM process. First, create the channel by anti-decomposition create channel system call. Then create proper resource by using anti-decomposition process channel batch buffer system call with create resource command. Next, set the proper value for the resource with command like set integer property or set float property or set buffer property and so on. Finally, calling anti-decomposition commit channel will serialize the data and send it to DWM process. In the DWM process, the vulnerability can occur while handling the serialized data. I think the vulnerability of DWM process is little different from normal Windows LPE. Typically, the normal Windows LPE is done by attacking kernel through the system call or attacking the system service through the LPC or RPC. However, the vulnerability in DWM process is fusion of them, sending the data using system call to attacking the system service. That is interesting part to me. Because DWM process is highly related with kernel, the direct composition, the differences between kernel and DWM process may make the bug. Because DWM process receives the data from kernel, so DWM assumes the data is already validated in kernel. However, if some values are only processed on the DWM process, so these values may not be validated in the kernel. Thus, this unvalidated value can make the problem. And the differences patch state can make also a bug. Because the kernel vulnerability will crash the system, so it can be found easier and will be fixed earlier. But if the patch does not apply to the both sides, the mismatch between kernel and DWM process may make the security problem. So let's take a look by the real vulnerability. The CV 2021-28310 is used for the real attack by Bitter APT group. This vulnerability is the out-of-bound access, which is caused by the patch differences between kernel and DWM. Because it is in the wild vulnerability, you can refer the Kaspersky report. To explain this vulnerability, I think the CV 2019-1041 is needed. This vulnerability is used on the point-to-on for the Windows LPE entry, and this vulnerability triggers the out-of-bound access in the Win32k driver. As shown in this picture, there is no validation for the property ID value. Thus, users can trigger the out-of-bound access in the kernel by just manipulating the property ID value. So the patch validates the property ID does not exceed the total count. Let's check the code of DWM. There is no patch applied, so DWM does not check the property ID. But property ID value is already validated in the kernel. So how can I trigger this vulnerability? As shown before, this code says the only successful command will send to DWM. So let's see more code in kernel. When will the command be failed? First, when the adding entry is failed, and second, when the value is invalid. What happened if the entry is added successful, but the value is not valid? Then the number of entries in kernel will increase, but this command will not be sent to DWM. It can make the different structure between kernel and DWM. These differences will make the out-of-bound access in DWM. I will show you how this vulnerability is triggered. First, add two valid entries and commit the data. The status of kernel and DWM is like that. And then add 100 entries with invalid offset and ID value. The number of entries in kernel will increase, while the number of entries in DWM will not, because the command was not sent to DWM. In this situation, update entry of large index will trigger out-of-bound access in the DWM process. So how can we exploit this out-of-bound access? Let's check the code that writes value. From this code, we can guess the structure of C property set object. As shown, this is code. This object has properties data pointer and properties array. So we can guess like that the structure of C property set object. And there are two arrays. One has offsets and types, and the other has the data. After getting the offset from the properties array by property ID and write the value to the region offset away from properties data. By the vulnerability, we can send Raji property ID value. So to use this write primitive, we should locate our data after the properties area to manipulate the offset value. And we also should place the target object after the properties data area. But how can I locate our data into out-of-bound area? To locate our data into proper location, we need to groom the heap as we want. To make the heap layout correctly, the more detailed C property set object structure is needed. You can get this structure by reverse engineering. Maybe it is similar to what I guess. The important part of this structure is the size and the alignment of C property set object and properties array and properties data array. In Windows, the same size objects are located at the same page. So controlling the size is very important for making the memory layout. First, the size of C property set object is fixed as 0x98 bytes. And how can it control the size of properties and properties data array? In the property set object, there are many kinds of data. This picture shows the several kinds of data like D2D matrix or bool or float and so on. Each data will increase the properties array by 8 bytes for offset and type. But properties data array will grow according to the type. For example, float will increase 4 bytes and D2D vector 2 will increase 8 bytes. Using this fact, I will make the memory layout by using these two types of objects. The spray object, which is used for spraying, has 0x40 float data. So the specification of this object, like the top picture, and the OOB object, which is used for triggering the vulnerability, has 0x1A float data and 6 D2D vector 2 data. So the specification of OOB object, like the bottom picture. So my strategy for making the memory layout is like that. First, spraying the spray object. Since the same size object will locate in the same area, the memory layout after spraying will be like this. And then allocate the OOB object. According to the size of OOB object, each data will be allocated like this. Finally, spray again. It will fill the free space, and the final memory layout will be this state. Because we can control the contents of properties data, arbitrary offset value can be injected. By this malicious offset, we can overwrite the data of C property set object. This is the real memory layout from WinDebugger. The data is nicely organized. The fake offset value is placed after the properties of OOB object. The right picture shows that. And the target object, C property set object, is adjacent to the properties data of OOB object. The left picture shows that. So now, what data is good to overwrite? Maybe you can know just overwriting the pointer of properties data in C property set object and update the value will make the arbitrary write primitive. So properties data pointer is the best target. Now, we can get an arbitrary write primitive. From here, there are lots of ways to change the control flow. In this presentation, for controlling the flow, I use additional virtual function call, which is called after updating the value. This function call uses the object that is located at offset 0x48 in C property set object. And by this object, it do the virtual function call here. So I have controlled the execution by following these steps. First, write the fake object to the free space by using arbitrary write primitive. Second, change the address at 0x48 offset to the address of fake object by out-of-bound write primitive. And then, updating the value will trigger the arbitrary object call for the fake object. So we can call arbitrary function call with arbitrary data. So this is the final step. We should execute arbitrary code. Now we have arbitrary function call and arbitrary write primitive. Because of control flow guard mitigation, CFG, we can call the function which is valid for the CFG. In this exploit, I will use this function. The name is like this dxgr blah blah something destructor. It will call the load library from the path in global variable. This function was used for exploiting previous bug CWE 2020-1362. So after writing the path to the global variable, the DLL path C5E655 using arbitrary write primitive and call this function by using arbitrary function call primitive. It will make the code execution through load library API. So this is the demo video, and so executing the exploit, and we get the DWM user privilege, and that is system integrity. So it is the conclusion. Attacking system service by using the system core is interesting type of vulnerability. And the kernel and DWM process is highly connected. Because of this structure, the differences between kernel and DWM process can make vulnerability. I think applying the patch on both sides is easy to forget. DWM process is often crashed. You can recognize it by screen blink, then check the log and the problem. This is trivia. I have also prepared the CVE 2022-38050, which is also the vulnerability of DWM process. However, the content is deleted due to the time problem. So I just attached the exploit object for this vulnerability to commemorate my deleted contents. My presentation is ended. And if you have, you can use the email address if you have question. And thank you for listening to my presentation.